Hello everyone, welcome back to the Microservices Masterclass series. In the previous episode, we discussed different way in which microservices communicate. But communication is only one part of architecture. Every microservice also need to store and manage its data. And this creates some important questions. Should all microservices connect to one common database? Or should every service have its own database? Why should we allowed to update the data? Sorry, who should be allowed to update the data? And can different services use different database technology? In this video, we will answer these questions and understand the basic data management pattern used in microservices. So let's begin with comparison shown at the top of the diagram. Understanding the main diagram, considering an e-commerce application with three microservices: order service, inventory service, and payment service. On the left side, all three services are connected to one common database. This is called shared database approach. On the right side, every service has its own database. Order service on the order database, inventory service on the inventory database, and payment service on the payment database. This is called database per service pattern. At first, the shared database may look simpler because every service can access all the data directly. However, it creates tight coupling between services. Database per service provides better independence and clear ownership, but it also introduces challenges related to queries, transaction, and data synchronization. Now let's understand every section of diagram step by step. Why data is hard in microservices? In a monolithic application, different modules usually use the same database, and the order module can directly join the order table with inventory and the payment tables. A simple database transaction can also update multiple tables because everything is stored in one place. Querying and maintaining consistency is relatively straightforward. Microservices work differently. Every service should be independently developed, deployed, and scaled, but business data is still connected. For example, when a consumer places an order, the order service creates the order, inventory service receives the product, payment service processes the payment. These are three independent services, but all of them participate in the same business process. Therefore, the main challenge is how do we keep business data consistent without tightly coupling the services? If services share all their data directly, they lose independence. But if their data is completely separated, queries and transactions become more difficult. This balance between data consistency and data service independence make data management one of the most challenging part of the microservice. Now let's understand database per service. In the database per service diagram, every service owns the and controls its data. The order service stores data related information in order service. Inventory service stores stock and reservation information in inventory service. The payment service stores payment transaction in payment database. The important rule is a service database should be accessed only through that service. For example, the order service should not directly query the inventory database. If it needs information, it should call the inventory service API and use an event published by the inventory service. Similarly, the payment service should not directly update the order database after completing the payment. Instead, it should send a payment complete event or call an API provided by the order service. It gives each service the freedom to change its internal table without affecting other services. The inventories team can redesign its database, add indexes, rename internal tables, and even change the database technology. As long as the external API and event remain compatible, other services do not need to know about these internal changes. This is the main advantage of database per service, independent ownership and independent changes. Next is shared database NT pattern. Now let's look at the left side of the diagram. Here order service, inventory service and payment service are connected to one shared database. Initially this looks convenient. The order service can directly query inventory, the payment service can directly read the order, and reporting query can join all three tables. But this convenience creates tight coupling. Suppose the order service directly reads the inventory table. Now it depends on the internal table structure owned by inventory service. If the inventory team renames a column or change the table structure, the order service may fail. This is not serious problem. There is another serious problem. One service may directly update another service data. For example, order service may directly reduce the inventory quantity. But inventory management may contain several business rules. Check availability stock, reserve items, prevent negative inventory, handle warehouse selections, release expired reservation. If the order service directly update the inventory table, it can bypass these rules. Okay, a shared database also makes independent deployment, security, scaling, and failure isolation more difficult. The application may contain separate services, but the shared database keep them tightly connected. This solution is often called distributed monolith. That is why a shared database is generally considered as an NT pattern when building a truly independent microservices. Data ownership. The database per service is not only about creating multiple databases. The deeper principle is data ownership. Every business entity should have one clear owner owning service. For example, order service owns the service orders, inventory service owns the stock, payment service owns the payment, and customer service owns the customer profile. The owning service becomes the source of truth for that data. Only the owning service should directly write to its database. Suppose a payment is completed, the payment service should not directly update the order table. The payment service should not update directly the order table. Instead, it communicates the result to the order service, and the order service then applies its business rules and update the order status. Why is this important? Imagine an order cannot be confirmed after it has already been cancelled. This validation belongs to the order service. If the payment service directly updates the order, it may bypass this violation and create an invalid order state. Or other services may keep a copy of same order information, but ownership remain with the order service. Clear ownership ensures that business rules are applied consistently and changes remain controlled. Data isolation options. Does database per service means every service must have completely separate physical database service? Not necessarily. There are three common isolation options. Private table. In the first option, services use the same database but each service owns a separate set of tables. For example, order service owns the order tables, inventory service owns the inventory tables, payment service owns the payment table. This is simple and less expensive, but isolation is weak. Without proper permission, one service may still access another service table. The second is private schema. Second option, to create and separate schema for each service. For example, order service, inventory schema, payment service. Each service can have separate database, user with permission to access only its schema. This provides stronger logical isolation. Separate database. The third option is separate database. It provides a completely separate database for every service. This offers a strongest isolation. Each database can be scaled, secured, and backed up and monitored independently. However, it also increases infrastructure and operational complexity. The correct choice depends on system size, security requirement, traffic, team structure, and cost. The key principle is exclusive ownership, not necessarily a separate physical server from the first day. The next point is poly- polyglot persistence. Only, sorry, once every service owns its database, it can select the database technology that best match its requirement. This is called polyglot persistence. For example, order service may use PostgreSQL because the processing requires relational data and transaction. The product catalog service may use a document database because different product can have a different attribute. The cart service may use the Redis because shopping cart data requires very fast access and can be temporary. The search service may use OpenSearch because it requires a full text searching and filtering. This flexibility is useful, but it should be used carefully. Every new database technology requires additional expertise, monitoring, backup and recovering, security configuration, infrastructure support, maintenance effort. Do not choose a different database only because microservices allow it. Choose only when it provides a clear advantage for that service. Otherwise, standardizing on a familiar database may be simpler and more reliable. Data duplication. In traditional database design, we usually try to avoid duplicate data. But in a microservice, some controlled duplication is normal, sometimes necessary. Suppose the order service needs to display the product name with an order. It could call the product service every time someone view the order, but it creates an additional network call and runtime dependency. If the product service is unavailable, the order service may not be able to display the complete order. Instead, order service can store the product name when the order is created, and now product name exists in both product service and order service. But these copies have different purpose. Product service owns the current product information. The order service stores the historical snapshot of the product that was purchased. Similarly, the notification service may also only the customer's email address required for sending the message. The rule is replicate only the data that is service genuinely need for its own responsibility. Do not copy complete database unnecessary, and also remember that duplicated data may become temporarily stale. Services can synchronize this data using events, which we will discuss in part 2. Production best practices. Let's finally look at some practical best practices. First, define service boundaries according to the business capability. Second, clearly document which service owns each important business entity. Third, never allow one service to directly update another service database. Use API or events for communication. Fourth, enforce ownership using database users, permissions, schema, and network rules. Do not depend only on the developer discipline. Fifth, choose the appropriate level of isolation. Private table may work for a small system, while separate database may be required for larger and security sensitive systems. Sixth is use polyglot persistence carefully. Prefer the simplest database that correctly solve the service requirement. 7. Duplicate only minimum required data and define how the data will be synchronized. Finally, independently monitor database performance, connection usage, storage, backup, replication delay, query failure, availability. These best practices help maintain clear boundaries while keeping the system reliable. So quickly recap the complete diagram. Data management is difficult because independent services still need consistent business data. Database per service pattern give every service ownership and control over its data. The shared database creates tight coupling and may turn microservices into distributed monolithic. Only the owning service and should directly write its data. Data can isolated using private table, private schema, and separate database. Polyglot Persistent allows service to choose SQL, NoSQL, Redis, and search database according to their needs. And control data duplication can reduce runtime dependency. But one important question remains: if every service owns a separate database, how can we query and synchronize information across multiple services? This is exactly we will discuss in episode 14 part 2. If you found this video useful, please like the video, subscribe to my channel, and share it with your anyone learning who is microservices and system design. Thank you for watching. I'll see you in the next episode of the Microservice Masterclass. Thank you. Bye bye.